All right, guys, so we're going to complete topics 3.9, 3.11, and 3.12 today. So it's really a topic or topics that are about intermolecular forces. So intermolecular forces are attractions between particles. We've talked about these and called them dipole-dipole interactions. We've talked about hydrogen bonding. We've talked about London dispersion forces. And we've come to the conclusion that there's going to be attractions between molecules always, or between atoms and atoms always. But the strength of those forces is going to be different depending on what type of attraction you are working with. Now, when you're talking about a solution is a homogeneous mixture. So it's got components that have different intermolecular forces binding them together. So you can use these different intermolecular forces to separate components of a solution or of a homogeneous mixture. The way that you can figure out what separation technique will be best is by knowing what types of intermolecular forces are present in the solution. So is it hydrogen bonding or is it just London dispersion forces? Because those have very different strengths. That would help you identify what separation technique would be best for that particular solution. So we've got a few pictures here for some relevant applications to this lesson. So the first picture right here is kind of hard to read. This is distilled water. So distilled water is referring to pure H2O. There are absolutely no impurities or other components to it. It is not a mixture at all. It's a pure substance. Every single molecule and particle in that water is going to be two hydrogens and one oxygen bonded together. Now, it sounds too good to be true that it would be pure and that there wouldn't be any impurities in there. And the way that it is not developed, but the way that it is produced is through a separation technique of separating pure water from other impurities and components that are usually in water when you get it from a spring or from a lake or from the ocean. There are all kinds of impurities in there, but you can separate them out using a process called distillation, hence pure water being called distilled water because it's gone through this process of distillation. We've got this next picture right here. This is an image of the flame test, and each of these flames is actually being produced from a different element. So this first flame is being produced from lithium. The next flame is being produced from strontium. This yellow flame is from sodium. This green flame, sorry, I had to read real close, is from copper. And then the last flame is from potassium. So each element is producing a different color. And this has to do with electromagnetic spectrums and electrons when they're absorbing energy, jumping from one level to another. And this is a way also to separate components even in a mixture. And then this last method, you may have seen it in your biology class, is chromatography. So chromatography is used often to separate components of leaves to figure out what produces the pigments that we see in different colors in different seasons in leaves and in plant life. So it also helps us determine different components in cells too. What exactly allows plants to photosynthesize, because that color change has to do with their ability to photosynthesize based off of the time of year. So all of these different separation techniques have to do with what I highlighted right here, intermolecular forces. So this topic fits, or these topics fit really well into this unit because all we've been talking about all unit long is intermolecular forces. So moving on to the next slide. The two most popular methods of separating mixtures are chromatography and distillation. Chromatography, sorry, my spelling is always the best. Chromatography and distillation. So we've got three images right here that are showing different separation techniques. So the first one is showing what chromatography looks like. The most popular method of chromatography is paper chromatography. So I'm going to put down below here, this is paper chromatography. So you may have noticed, like when you're cleaning with a paper towel, that paper towels are very absorbent, but paper is too. When you put paper in a liquid, you will see that the liquid starts to move through the paper. So we can use that to observe phenomenon of things within that liquid separating. So in this image right here, we've got a piece of paper that's being hung into a solvent, and as that solvent is moving up the paper, we're seeing separations of the components of the mixture, which we can use that data and that evidence to really identify some of the properties of those components. This middle separation technique is distillation. You've seen this before when we've talked about separating mixtures before as a plausible method to do this. We'll talk a little bit more about what each of the pieces are in this distillation separation technique, but you've seen this also in the YouTube video by Tyler Dewitt, and he talks a little bit about the different parts too. This last separation technique is filtration, and I included it in here because it is not a good method. It is a poor method of separation for a solution. In fact, it doesn't actually separate components of a solution because filtration depends on having a solid residue. So I'm going to highlight this term right here, a filtered solid residue. So filtration works really well for, an example would be water that has some sand or some dirt in it. If you're trying to mine gold and you've ever done that fool's gold mining activity, you can filter out those solid pieces from your solution or your mixture, and it'll get caught on that either filter paper or whatever you're using for a filter. In chemistry, we'll typically use filter paper because the particulate nature that we're looking at is usually small, very, very small, but it can be caught on filter paper. We don't need something that's very large to filter it out. But it doesn't work very well when you're referring to a liquid and a liquid that are mixed together. So it works great for a liquid and an insoluble solid. So insoluble is a word that you're familiar with, but I'm going to remind you what it means. Insoluble means that it doesn't dissolve. So sometimes you'll mix a solid and a liquid like sugar and water and salt and water, and that solid is going to dissolve, which would disqualify it from working for filtration, because both the salts and the water, or the sugar and the water, would pass through the filter. So you really need a solid that hasn't dissolved in your solution to be able to filter it out. So moving on to the next slide. We're going to talk a lot more about chromatography. Now, you should have watched a video on chromatography already, so you should have quite a bit of background on this. So I'm going to try to not spend too much time going over it, and I'm really going to just talk about the very important topics that the AP exam is going to expect you to know, that the College Board is going to expect you to know. So chromatography consists of two phases, a moving phase and a stationary phase. Now, since the most popular form of chromatography is paper chromatography, that's what I'm going to refer back to quite frequently. So your stationary phase, when you're referring to paper chromatography, is the paper. Stationary means it's not moving. So the paper is not moving. If we think back to that picture that was down here below, the paper is stationary. What's moving is your solvent or your liquid that is moving through the paper. Now, normally, you're going to see a difference in intermolecular forces between your moving and your stationary phases. Now, paper is polar, which would mean that ideally for paper chromatography, the liquid, the moving phase, would be nonpolar, so that you can see a difference in intermolecular reactions. So, yes, not reactions, forces, intermolecular forces. So when a solution is exposed to a stationary and a moving phase, each component of that mixture, so when I'm talking about mixture component, Maybe we could talk about a beaker filled with water that has sugar dissolved in it and salt. Those are two very different components, but both of them dissolve in water. So we've got sugar, salt, water solution. So sugar is one component, salt is another component. Each of these components or solutes will experience either a greater or lesser affinity to the phases. Now, affinity might be an unfamiliar word, so I'm going to talk about what I mean by that. Affinity is kind of like an attraction. Actually, it is an attraction. So when something has a great affinity to something else, that means it has a great attraction to it. If it's got a lesser affinity, that means it is not attracted. So components with a higher affinity are going to experience a greater intermolecular attraction. Remember, we're thinking about this in terms of those molecules, those particles. So let's say sugar is experiencing a weak affinity or a lesser affinity. That means that it's going to have lesser intermolecular attractions. So higher affinity means greater attractions, lesser affinity means weaker intermolecular attractions. And we're going to be able to observe this with the movement of these components across the paper. So on the next slide, I'm going to show you guys what I mean by this. So we've got this image right here, and it's got all of our different components moving across the paper. Now I'm going to zoom in so we can see what some of these labels are. So we've got this line down here at the very bottom of our paper. We call it our baseline. This is the first site of the mixtures movement. So this is kind of like your starting point for your mixture. So you can say everything was moving from here. Now, as the components start to separate, we're going to see properties of those components. So this is showing an example of a mixture that's got different dyes in it. So we've got dye 1, dye 2, and dye 3. I can see where dye 1, I'm going to color in the same color that they have. Dye 1 is blue. I can see where dye 1 is because first of all, it's the same color and it's the same distance away from the baseline. I can see where dye 3 is because it's red. So these are the same color, so I know they're both the same dye and they're the same distance away from the baseline. So I know I'm looking at molecules that have the same identity. And then dye 2 is my yellow, and it's actually only one of these markings on the paper, but I can tell that it's dye 2 because it matches in color. So the farther that a component travels, so for example, dye 3. So the farther the movement means that that component is more attracted to the moving phase. So the farther the movement, the higher the affinity to the moving phase. So if this component has a higher affinity to the moving phase, that means it has a greater attraction to the moving phase. Now there's another way that you could think of this too. So we could say, okay, because it's moving with the moving phase and it's going farther, that means it's sticking with the moving phase farther. So we could attribute that to it being attracted to the moving phase. We could also say that it's unattracted or maybe even repelled from the stationary phase. So there's two ways we can think of this. Greater attraction to the moving phase, or weaker attraction to the stationary phase. So I'm going to say and/or, because both of these things could be happening. It could be a greater attraction to the moving phase and a weaker attraction to the stationary phase, or a weaker attraction to the stationary phase. So if I knew the polarity of my moving phase and my stationary phase. I can make some assumptions about the polarity of my components as they moved based off of how far they moved. So once again, in the margin, I'm going to make a note here. Paper is polar, which means that the solvent that you're usually dipping in is going to be non-polar. So my red dye, or my dye 3, since it has a greater affinity to my solvent, it moves farther. That means that it's likely going to be non-polar. I'll write it in red because it's obviously very attracted to the solvent, and it's not attracted to the paper, which makes it non-polar. My substances down here, like my blue dye, must be a polar substance because it does not experience a great affinity to that moving phase, and it is experiencing a large affinity to the stationary phase. So it's essentially getting stuck to the paper because it's attracted to the paper. Whereas my yellow dye, or my middle dye, is probably somewhere literally in the middle for polarity. So maybe it's slightly polar, slightly non-polar. It would definitely have to have more polarity than the red dye though, because it didn't travel as far as the red dye. I'm going to rewrite this in a different color so that we can read it. So maybe medium polarity. Now we could quantify the distance traveled by each component from the baseline, as in we could measure it. We could see literally with a ruler, how far did the red dye travel versus how far did the blue dye travel? And we could see a quantifiable relationship between the length of travel and polarity. Even we could compare them. So there is a value called the retardation factor that compares the distance traveled by the component. So in this image, it would be traveled by one of the dyes, dye 1, dye 2, or dye 3. And we would compare it to the distance traveled by the whole solution. So it's just a part per whole. It's a fraction. So my solution is obviously going to travel the farthest because my solvent is going to travel the farthest, right? And then each component is going to travel some distance within that. So I could create a fraction and quantify the factor at which these components travel, and that's called the RF factor, the retardation factor. So moving on up in the world, next page, we're going to move on to the next type of separation method, which is distillation. So components in a mixture are going to boil at different temperatures. The likelihood of finding two substances with the same exact boiling point, I think, would be impossible because they'd have to be the same molecule and have the same exact intermolecular forces. So when we were first learning about intermolecular forces, we noticed that if there are strong attractions holding particles together, it's going to take a lot of energy, and yes, I'm bouncing my fists on purpose. It's going to take a lot of energy to break those attractions and separate those molecules. So the boiling points are going to be very, very high because this is essentially communicating we need a lot of energy. We've got to add a lot of energy to those molecules to give them enough kinetic energy to break their attractions. Whereas if there are weak intermolecular forces holding molecules together, I don't have to put a ton of energy in to separate them. So they will separate at a very low temperature. So they'll boil at a very low point. A distillation technique takes advantage of those differences. So we've got a couple of different parts to this. So this is called a volumetric flask. A volumetric flask is going to be round like this, kind of like a bowl, and it's going to hold a very specific amount of solution. And you'll be able to tell by the markings on the side how much solution is in there as long as you fill it to the line. We've got this piece right here called the condenser. The condenser is what allows the gas to condense back into the liquid phase. And it does this by pumping cold water in one end of the condenser, running it up, and then releasing it out the other side so that there is a constant flow of cold water. So the gas that's going through, I'm going to show in purple, the gas molecules that are going through the condenser are getting colder and colder and colder. And then by the time they get out here, so once they went into the condenser, they started as a gas. By the time they come out of the condenser, they're going to be in the liquid phase because they've lost so much energy from being in the presence of that cold water. So that liquid gets collected right here. So you usually have a collection beaker, but it looks like in this image they've got a collection graduated cylinder. Doesn't really matter as long as you're able to measure the amount that you've collected. So in the Tyler Do It video, he talks about how particles are going to boil at different temperatures, but he doesn't really talk about why. The College Board is really, really, really going to impress upon you that it has to do with those intermolecular forces. So the reason that distillation works, yes, is because substances have different boiling points. But the reason they have different boiling points is because they have different intermolecular forces holding them together. So your big takeaway, for distillation should be that it works because there are different intermolecular forces between molecules. Moving on to spectroscopy. So spectroscopy is kind of a mouthful. It's a lot of terminology. So I wanted to give you guys a formal definition and really break it down for you. So I'm going to highlight keywords, talk about what they mean so that you can get a really thorough understanding of what it is without me simplifying it too much. So spectroscopy is the study of the interaction of electromagnetic radiation and matter. Electromagnetic radiation is a fancy word or a fancy term for light. Specifically, and I guess not specifically, but broadly, all forms of light. So when we hear the word light, we probably think about visible light, the light from the light bulb, the light from your phone screen, the light you're seeing in your computer right now to watch this video. But there's all kinds of light that we take for granted, like radio waves. That's a form of light. It falls on our electromagnetic spectrum. Microwaves, a form of light. X-rays, a form of light. So ultraviolet rays, gosh, I could keep going. Infrared rays. I'm going to show you guys some images in a second that go through all of the different types that are really important for us. But any form of a wave, that is the transfer, the transfer of energy is going to be light and electromagnetic radiation. So the word interaction right here is talking about, what happens to matter when you bombard it with electromagnetic radiation. So absorption I'm losing my mind. Absorption spectroscopy involves a sample being exposed to radiation of varying types. So I just went through the fact that the electromagnetic radiation is all forms of light. This is talking about now, okay, this is the study of specific types. So what happens when I use a specific type of light over and over again? Do I see the same thing? Do I see different things? Is there a pattern that happens? And then observing what happens as it interacts with the radiation. So as we've seen with the flame test, when you expose matter to even the same types of radiation or the same types of photons, you don't necessarily always see the same output. So on our first picture, when we were looking at all of the different elements for the flame test, none of them produced the same exact color of light. They were similar in some cases, but never the same exact color. So interacts is really talking about what is produced by this interaction. What does the matter do when it's exposed to this radiation, aka light? So depending on the type of radiation used, information about the substances can be gathered. So you might be wondering what kind of information can be gathered. Information like what elements are present in this mixture or solution or even compound. What's the structure of the molecule look like? Some of you guys were asking questions when we were talking about molecular geometry. How do chemists know that, this is the actual shape of the molecule? Or how do they know that this molecule is preferred because of its formal charge? Where did they come up with that? Was it all theoretical, or do they actually have evidence? This is how they determine molecular shapes. And this is how they determine desirable or favorable structures. This is where formal charge came from and where resonance structures came from, by exposing matter to different types of light and seeing how does it react to that amount of energy, or that specific amount of energy. So the specific types of electromagnetic radiation that are useful are ultraviolet rays, UV rays, and visible spectroscopy, PES. You may be wondering, what the heck is that? Visible spectroscopy is Roy G. Biv, your visible light, which makes sense that they would call it visible. These wavelengths are relatively short. So remember, wavelengths are referred to in nanometers. So we're talking about, in the 100s, in the 200s, 300s, 400s, like really, really low, maybe all the way to like 700. In that range, very, very short wavelengths. The next type of radiation that's going to be valuable is the infrared spectroscopy. So your IR, your infrared range. This is where infrared goggles come from. And then they have a medium or intermediate wavelength. So in between UV and visible. And then our next one, which is microwave, which are relatively long. We use the word relatively here because there are definitely wavelengths that are longer, like radio waves, specifically X-rays, specifically, are much longer than microwaves. So while it is classified as a long wavelength, it's definitely not the longest that we could have. So moving on to the next slide, we're going to talk about how does matter react to each of these types of radiation. So for UV and visible photons, we tend to see electronic transitions. So electronic transitions is referring to electrons moving energy levels. So either jumping to a higher level or falling to a lower level. So this is where we would draw our Bohr diagrams, and we would draw photons going into the electron, and it would jump to a higher level, or it would fall to a lower level and it would release a photon. But these electronic transitions is really just referring to electron movement within the atom. So it can be used to gather information about electron configurations. And remember, electron configurations, if I had to write an example, is your 1s2, 2s2, 2p6, so on and so forth. If you ever wondered where the heck did we get data to show that there's 2 electrons in the 1s orbital and there's 2 electrons in 2s, but there's 6, I can hold up 6 fingers, 6 electrons in 2p. How did we get those numbers? It came from this, bombarding matter with UV and visible light, and really quantifying and recording how much energy is recorded or output from the matter during those electron transitions. And if there was always 6 times as much, that meant there was 6 times as many electrons jumping around. If there was a third as much, that meant that there was only 2 electrons jumping around as much. So infrared spectroscopy is going to really cause a change in the covalent bonds. So when those covalent bonds are exposed to energy or photons, what they're going to do is they're going to bend, stretch, and most importantly, vibrate. So think about a ball and stick model of a molecule. So what I mean by ball and stick is you've got one atom connected to another atom with this stick, and each atom is represented as a ball. This bond is a covalent bond that can bend, stretch, and vibrate. So when we would draw molecules in the solid phase, we draw these whooshies that go buzz, 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 buzz. Imagine that they're able to buzz, buzz within the molecule and get closer together buzz, buzz, and farther apart. This is what bending, stretching, and vibrating is referring to. And this gives us some really important data about bond lengths and different compounds, but specifically that type of covalent bond is determined by this vibration and bend. So single versus double versus triple bonds have been determined with infrared radiation. Now, the last radiation or electromagnetic spectrum wave that we bombard matter with is the microwave, and this produces molecule rotation. So this is what causes molecules to rotate in place. So they're not necessarily changing position, but this is what's causing them to spin in place, giving them that rotational motion. This allows us to determine not only just the chemical composition, aka what elements are present in a molecule, but it allows us to determine the structure of a molecule. So this could be answering a question along the lines of, how do I know if I have a molecule that is a chain of carbons versus a molecule that makes a hexagon of carbons? I think I drew an octagon instead of a hexagon, but this is what determines the shape, because a string of carbons is going to rotate with much more difficulty than a ring of carbons is going to rotate. So the energy input to get those two things to rotate is going to be very different, but by telling or comparing the energy input, we can make an inference as to what the shape or the structure of the molecule is going to look like. So I've been talking about how, if we were to take quantifiable data, if we were to have numbers, or if we were to compare the numbers, we would be able to make some inferences. This is how you get numerical values from this. And we've actually learned this before when we talked about electromagnetic spectrum before in Unit 1, but photons have an energy associated with them that we can calculate using these two equations. So what's odd is that light all travels at the same speed, the speed of light, which is 3.0 times 10 to the 8th meters per second. But not all waves or light have the same wavelength. So we can have light with a very wide wavelength, and we can have light with a very short wavelength. Depending on the wavelength, that's going to change how many waves pass by a single point. If I were to mark it, a single point per second. If it's a longer wavelength, and it is going at the same speed as another wave, it's going to have a much shorter frequency. So you can think of this as this wave is going to not pass as many waves through this line as frequently as a wave that is shorter is going to pass at the same point. So we can use that data for the speed, the wavelength, and the frequency to calculate the energy. So we can use this equation right here to find the energy of the wave. So the energy of light, or the energy of a photon, or the energy of the wave, is going to be equivalent to Planck's constant times the frequency of that wave. Now, Planck's constant is very different from the speed of light. It is 6.62608 times 10 to the negative 34th joules times seconds. Now, don't feel concerned that you have to know these values by heart. You really do not. I don't even know them by heart. I know the speed of light by heart, but that's just because I've done so many calculations with it, and it's a much nicer number to remember than Planck's constant. Both of these equations and both of these constants are going to be on your formula sheet. So this is where it's going to be really important that you have that formula sheet for AP Chem somewhere handy. you can print it out from the agenda, or you can keep it on the computer or keep it on your phone, whatever is going to be more convenient for you. But the AP exam is not going to give you a warning saying, hey, by the way, you need this equation, or hey, by the way, you need this constant. It's going to be on you to infer, okay, I need to do a calculation to find a specific value. These equations will help me get there. So on the homework, be prepared to have to infer when you're going to have to use an equation or not use an equation. Usually if they're giving you numerical values having to do with wavelength or with frequency, or they're asking you questions about energy, you're going to need these two equations. The one warning that I will give you is to watch your units constantly watch your units. What I mean by that is your speed of light is in meters per second, not nanometers per second. But what you'll find is that your wavelengths are typically given to you as nanometers. You're going to have to convert nanometers into meters before you plug into this equation. So you'll need to know that 1 nanometer is the same thing as 10 to the negative 9th meters. Or another way of thinking of it is that 10 to the 9th nanometers is equivalent to 1 meter. Both of these conversion factors will allow you to convert back and forth from nanometers to meters. So for example, if I was working with a wave or a photon that had a length of 450 nanometers, and I wanted to figure out what is the frequency of this wavelength, I would have to convert nanometers into meters. And I could do that with either of these conversion factors. I would know that nanometers would need to cancel out, so it would need to be in the denominator, and meters is what I'm trying to get to, so it would be in the numerator. Now, whether I choose to do 10 to the negative 9th meters for every 1 nanometer, or I choose the other conversion factor, 1 meter is the same thing as 10 to the 9th nanometers. These are two mathematically equivalent fractions, because 10 to the negative 9th is literally the same thing. I'm going to highlight it. 10 to the negative 9th is literally the same thing as 1 over 10 to the 9th. So regardless, you will still get the same quantity no matter which one you use. So I would suggest using the conversion factor that you can easily commit to memory and is the least confusing for you to think about, because this information is actually not on your equations and constants and formula sheets. So you will be held accountable to know that by heart. So let me know if you have questions or concerns on the homework. I'm more than happy to give you feedback as best as I can. So have a great rest of your day.